Hello, my name is Wojciech Hozga and I work at IBM Research in Zurich. Today I will present our work on remote attestation of the virtual machine's runtime integrity in public clouds. This is a result of cooperation between IBM Research and Technical University of Dresden. In summary, we show a method to record, report, and enforce the virtual machine's runtime integrity in public clouds. The cloud computing defines two actors, the tenant and the cloud provider. The tenant owns applications and he requires computing resources to execute them. These computing resources are provided by the cloud provider, whose business is to maintain and rent them. The tenant pays the cloud provider a certain amount of money for renting enough computing resources to run his applications. For the duration of the rent, the cloud provider gives the tenant access to the rented computers running in his dataset. The tenant deploys his applications on the provisioned computer. Although the computer looks like a regular physical computer, in reality it's a virtual machine running on a physical computer. There are three reasons why the cloud provider gives the tenant a virtual machine instead of the entire physical machine. First, from the functionality point of view, there is no difference between a virtual machine and a physical computer. Second, it's easier to manage virtual machines than physical computers. The cloud provider can dynamically and rapidly, within seconds, create computers with required amount of CPU cores, memory, and disk space. And third, the tenant can easily scale up and down his application by decreasing or increasing the amount of computing resources while paying accordingly to the utilized resources. It's the virtualization technology that allows for splitting physical computer resources into virtual machines. The virtualization requires a dedicated layer of privileged software called hypervisor to manage virtual machines. The hypervisor provides virtual machines with access to physical resources, isolates them from each other, and controls their lifecycle. From the tenant's point of view, it's essential to ensure that correct hypervisor controls the virtual machine, because the virtual machine's security depends on the hypervisor. For example, an adversary who gets in the control of the hypervisor can introspect the virtual machine's memory, reading the confidential data processed by the application. She can compromise the tenant's application by tampering with the hypervisor's configuration or the virtual machine deployment. Even when the hypervisor is legitimate, an adversary residing outside the cloud can compromise the application's integrity and confidentiality. She can exploit a guest operating system misconfiguration, or she can use social engineering to connect to the tenant's virtual machine remotely. Then it's enough that she runs dedicated software or she boots custom kernel to impersonate the virtual machine and get long-term access to the virtual machine while maintaining full access to the application and processed data. The problem we tackled is how to technically ensure that the cloud node and the virtual machine run only expected software in the expected configuration. This is an important problem because it allows for detection and prevention of certain class of attacks. It follows the trust path verify approach, where we trust the cloud provider to manage our computing resources, but we verify that these computing resources are indeed controlled by the expected software in the expected configuration. The proposed solution follows the Zero Trust security model principles, in which we authenticate machines and ensure their compliance to security policies. Finally, some domains like the financial or e-health systems must comply with regulations that require presence of certain security mechanisms like file integrity monitoring. So let me introduce you to TRIGLAV, a method to record, report, and enforce the virtual machine's integrity in the public cloud. TRIGLAV is a process running on the host operating system. Its main task is to record, report, and enforce the runtime integrity of the host and guest operating systems. TRIGLAV executes inside the trusted execution environment, such as Intel SGX, and relies on the trusted computing to establish trust with potentially untrusted host operating system. The tenant relies on TRIGLAV to attest to the virtual machines and host operating system's runtime integrity. TRIGLAV shares with the tenant a public portion of the SSH key. TRIGLAV enforces that only a legitimate virtual machine can access the private portion of the SSH key during the SSH handshake. That means that when a tenant establishes an SSH connection with the virtual machine will request TRIGLAV to sign an SSH challenge using the private portion of the SSH key it possesses. TRIGLAV will sign this challenge only if the recorded integrity measurements of the host and guest operating systems conform to the tenant's security requirements. Please note that the private portion of the SSH key never leaves TRIGLAV. TRIGLAV only signs the challenge on behalf of the legitimate virtual machine controlled by the legitimate host operating system. The signed challenge is returned to the virtual machine, which then uses it to prove to the tenant that the virtual machine and the host operating system are trustworthy. The natural question that arises is how TRIGLAV manages the SSH key. How is the key generated? How TRIGLAV decides that the virtual machine can or cannot access the key? Everything starts when the tenant deploys a security policy to TRIGLAV. From the tenant's point of view, TRIGLAV is initially the only trusted component running on potentially untrusted computer in the cloud. The tenant ensures he communicates with the legitimate TRIGLAV instance running inside the trusted execution environment on a genuine CPU using a remote attestation protocol. Once the tenant establishes trust with TRIGLAV, it sends to TRIGLAV the security policy. The security policy is a file containing a set of rules defining what is the expected integrity state of the hypervisor and the virtual machine. The policy is divided into two parts: the definitions of the host operating system and of the guest operating system. The first part reflects the contract between the tenant and the cloud provider. It's based on the cloud provider declaration on what is the expected host operating system configuration, what software builds it, and what security mechanisms it implements. The tenant relies on TRIGLAV to verify that the cloud provider indeed fulfills his promises, because TRIGLAV uses definitions from the security policy to decide whether or not the virtual machine is controlled by the expected host operating system. Here we assume that the cloud node is built from the software which source code is certified by a trusted third party or can be reviewed by tenants. The security policy defines what security element records the integrity measurements of the host operating system. The security element is a cryptographic device, such as trusted platform module or hardware security module, that offers tamper-resistant memory where integrity measurements are stored. It also offers the remote attestation protocol to certify the memory content. The security policy defines the load time integrity measurements of the kernel, and a certificate allowing for verifying runtime integrity measurements collected by integrity enforcement mechanisms such as Linux IMA. The second part of the security policy defines expected integrity state of the virtual machine. This part does not require any cooperation with the cloud provider because the tenant controls software running inside his virtual machine. The definition includes the load time integrity of the kernel loaded inside the virtual machine, possible wide list of static integrity measurements, and certificates allowing for verification of runtime integrity measurements. During the policy deployment, TRIGLAV generates a unique SSH key pair corresponding to the tenant's security policy. As a result of the deployed policy, the tenant receives the public portion of the SSH key, which allows him to verify that the virtual machine is controlled by TRIGLAV. Now, let's discuss how TRIGLAV collects and records integrity measurements. Load time integrity is a deterministic measurement of the kernel calculated during the boot process. The runtime integrity is the integrity of software, configuration files, and dynamic libraries loaded by the kernel to the memory during the operating system's runtime. The load time integrity informs us that the legitimate kernel with enabled integrity enforcement and auditing mechanism was used. It allows us to reason about the runtime integrity because starting from the trusted initial state, we rely on the kernel to measure, record, and enforce the runtime integrity of the operating system. In other words, we get insights into the integrity of the operating system during its execution. We rely on the TPM-compatible device to store and report integrity measurements securely. TPM is a standard of cryptographic devices widely available in personal and server computers. During the computer boot, the first piece of code loaded from read-only memory executes, and it measures the UEFI boot component, stores the measurement in the TPM, and executes this component. This procedure is repeated sequentially for other UEFI components and bootloaders. In TRIGLAV, we use tboot, which is a bootloader that leverages dynamic root of trust for measurement, like Intel TXT, to measure and store the integrity of the kernel. Dynamic root of trust for measurement, so DRTM in short, creates an isolated execution environment where it executes the tboot loader securely. This guarantees the load time integrity of the kernel regardless of the trustworthiness of other software executed on the computer. TRIGLAV might also rely on a regular TPM-supported secure boot because it provides the boot time integrity measurement and enforcement. However, it comes at the cost of larger trusted computing base. Once the kernel is loaded, we talk about the runtime integrity measurements. Specifically, the kernel measures each user space process, configuration file, or dynamic library before it's loaded to the memory. The kernel verifies the hash using signatures stored in the extended attributes of the file system. If the hash does not match the signature, the file is not loaded to the memory. This prevents loading to the memory malware or misconfiguring the system. TRIGLAV is also a user space process. Before it executes, the kernel measures it and verifies that the measurement hash matches the signature. In such a case, the kernel stores the measurement in the TPM and loads the executable to the memory and executes it. The same procedure repeats for all files, including the virtual machine monitor executable. Once the virtual machine monitor executes, it launches a new virtual machine. The virtual machine starts a regular boot process where load time integrity measurements are collected and stored in a TPM-compatible device exposed to the virtual machine by the hypervisor. Specifically, TRIGLAV emulates the TPM device inside an SGX enclave and exposes it with the help of the virtual machine monitor to the virtual machine. TRIGLAV implements additional security measures to protect the emulated TPM from the rollback and man-in-the-middle attacks. Please see the paper for more details. Eventually, the virtual machine kernel is loaded, and at this time, we start talking about the runtime integrity of the virtual machine. Similarly to the kernel in the host operating system, the kernel inside the virtual machine measures all executables, configuration files, and dynamic libraries before they are loaded to the memory. The measurements are stored in TRIGLAV. Depending on the configuration, TRIGLAV can verify the measurement against the whitelist or a signature and instruct the kernel to execute or reject the executable. We implemented TRIGLAV on the Linux kernel. And we used Alpine Linux as the host operating system because it's designed for security and simplicity. It consists of a minimum amount of software required to provide a fully functional operating system that permits keeping a trusted computing base low. All user space binaries are compiled as position-independent executables with stack smashing protection and the relocation read-only memory corruption mitigation techniques. The TRIGLAV functionality is split into 3 modules. The monitoring service collects integrity measurements of the host and guest operating systems. It also exposes the REST API on which it receives the security policies from tenants. Our implementation relies on the Trusted Platform module as a secure element recording integrity measurements. Specifically, TRIGLAV reads these measurements via an untrusted TPM driver and from the Linux IMA, which is an integrity enforcement mechanism implemented as part of the Linux kernel. To protect TRIGLAV from initially untrusted host operating system, TRIGLAV executes inside an SGX enclave. Our implementation relies on Intel TXT, which is the implementation of the dynamic root of trust for measurement technology on Intel CPU. We use KVM QEMU to enable virtualization and virtual machine management. Each virtual machine accesses a dedicated TPM device, which in reality is a software-based TPM emulator executing inside the SGX enclave. This TPM device receives integrity measurements from the virtual machine's boot components and from the Linux IMA during the operating system runtime. The SSH key is stored inside the emulated TPM. The SSH server uses a PKCS11 protocol to use this key during the SSH handshake. TRIGLAV implements also a monotonic counter service. This service can run on a remote machine and is used to provide access to a monotonic counter. The TRIGLAV's emulated TPM uses the monotonic counter service to protect itself against rollbacks attack. We performed a series of experiments to evaluate TRIGLAV, and in this talk I will present two experiments in which we evaluated the impact of TRIGLAV on performance and scalability of real-world systems executing in the cloud. The first experiment shows the latency throughput ratio of the NGINX server. The NGINX server is a popular web server used for web hosting and load balancing. The x-axis shows the throughput in thousands of requests handled by the server per second. The y-axis shows the latency in seconds. So how much time does it take to the server to handle a single request? The native experiment shows that an NGINX running on bare metal without any security protection achieved the throughput of almost 75,000 requests per second. The next variant shows that NGINX running on bare metal inside an SGX enclave achieved almost 41,000 requests per second. We leveraged the SCON framework to run NGINX in the SGX enclave. Please note that TRIGLAV operates under a weaker threat model than SCON. We compare both systems to show the trade-off between the security and performance. NGINX running inside a virtual machine not protected by any integrity enforcement mechanisms and not attached to any TPM achieved almost native performance, 74,000 requests per second. Finally, NGINX executing inside a virtual machine protected by TRIGLAV achieved 70,000 requests per second. This is about 94% of the native throughput. Comparing to SCON, TRIGLAV achieved much better performance at the cost of much larger trusted computing base. The next experiment demonstrates the TRIGLAV scalability. We benchmarked the memcached server, which is a cache system commonly used in the cloud. We measured its throughput latency ratio depending on the number of concurrently running virtual machines. The x-axis shows the throughput in thousands of requests per second, while the y-axis shows the latency in milliseconds. We compared the execution of memcached running inside the virtual machine with and without TRIGLAV. We calculate the performance degradation between the variant with and without TRIGLAV, each time on different number of concurrently running virtual machines. When two virtual machines run concurrently, memcached running inside the virtual machine protected by TRIGLAV achieved 96% of the native throughput. When we used 3 virtual machines, we achieved 97% of the native throughput. And when we used 4 virtual machines, we also achieved 97% of the native throughput. So all in all, we observed up to 4% of performance degradation when protecting the virtual machine with TRIGLAV compared to native memcached execution inside the virtual machine, despite more virtual machines run concurrently on the host operating system. We argue that the evaluated system protected by TRIGLAV scale well with the number of concurrently running virtual machines. In summary, TRIGLAV is a method allowing for verification that the virtual machine is composed of and controlled by expected software in the expected configuration. TRIGLAV provides transparent support for legacy applications. It requires no changes in the virtual machine configuration. It permits tenant to remotely attest to the platform runtime integrity. It incurs low performance overhead. Thank you, and I'm happy to answer your questions.